Ketones and aldehydes are very good electrophiles, as you saw when you read the introduction portions of this chapter. And so that's probably their main way of reacting, is as an electrophile with a certain nucleophiles. So let's take a look at their reactions with oxygen nucleophiles. And one of the first one we want to look at is forming the hydrate, which, as you might guess from the name, is essentially adding water to our CO double bond. Just like when we add water to a CC double bond, we're essentially going to add OH to one side and H to the other. But in this case, because we started with an O, we end up with two OHs. So this is called a hydrate. And that is in equilibrium. You can take the hydrate back to the ketone plus water. We can do that using base or acid. So let's look at the base catalyzed first. So of course we are talking about aldehydes and ketones as a nucleophile. I'd like to point out that I'm using an ketone in these cases, but you can certainly draw an aldehyde and get the same mechanism. So there I've added OH minus, and I've pushed electrons onto the carbonyl O. And the last step then, it would be a proton transfer from water to regenerate the base and give us our hydrate, which is the same hydrate I drew earlier in this video. So that's the base catalyzed mechanism. We can also do acid catalyzed. And same ketone, water, H3O plus. Oftentimes we will protonate the ketone or aldehyde, which gives us a full positive charge on the O. That's a much better electrophile. And that allows us then to add water or other nucleophiles to the carbonyl carbon. You'll see that there's a final proton transfer step required here before we can get to the hydrate. And I'm just going to draw an arrow up here because it's the same hydrate. I'm going to use H2O to remove my extra hydrogen, and we've made the hydrate in this fashion as well. I'd like to point out that in the acid catalyzed mechanism, no anions are present. You may have heard me talk about fun with acid problems. This is one of them. We have acid. We've got a weak nucleophile. There are no anions present. I did not use base. I did not bring in an O minus. I did not create an O minus here. You should not be creating any negative charges in your acid catalyzed mechanism. The only negative charge that might be permissible is the chloride counterion to our acid that we made here by mixing HCl with water. That would be a permissible anion. It should just sit around and do nothing. So there's really no reason to draw it. But there's no anions present in this acid catalyzed mechanism. And conversely, there are no cations present in this base catalyzed mechanism. We've got a negatively charged OH minus, the base. It produces a new O minus on our ketone, and then this final proton transfer step, removing a proton from water, regenerates the base. It regenerates the minus. You should not be putting any plus charges anywhere in here unless you consider the sodium counterion for this OH minus, which we sometimes will put in, but most of the time we won't. All right, let's look at another mechanism, and it's a slightly more exciting mechanism than the hydrate, and this is the acetal formation. And this is going to introduce a mechanism that we will slightly modify from many other possible products in this chapter. So when we take a ketone or an aldehyde and we react it with an alcohol, not water, using acid catalyst, we can make what we call an acetal. And generically, this is an acetal. So the acetal has two OR groups in place of the carbonyl, the CO. And of course there is a water byproduct here. And so we can use either H2SO4 or tosic acid. Tosic acid is basically an organic soluble version of sulfuric acid. So that's tosic acid. You should recognize that as being very similar in acidity and structure to sulfuric acid, except of course we have this aromatic ring that makes it more organic soluble, which makes it a little easier for it to react with organic type molecules. So let's look at the mechanism here. It's very interesting. At first it looks very complex, but I think it is relatively straightforward and it should be easily mastered. So the first step, of course, is to protonate the ketone or aldehyde. And again, this works with aldehydes just as well. In fact, maybe it works a little quicker with aldehydes because they are a little more reactive. So we have a proton transfer where the ketone attacks the acidic hydrogen on the tosic acid or on the H2SO4. It produces a better electrophile in this case. And now we are ready to take our nucleophile. Remember that ethanol or any alcohol is a weak nucleophile. And so it needs some help. And the help comes in the form of the acid protonation step from step 1. So the acid makes a better electrophile. Our weak nucleophile can better react with that better electrophile. And now we get this intermediate here. And if we proton transfer, I'm going to use ethanol as a weak base to proton transfer. I can make a neutral intermediate. Remember, our goal is to get 2 O-ethyl groups. We are halfway there. And I'm going to draw this protonated ethanol because I'm going to use that proton to put it onto the OH that I have here so that I can make water. So here I had a proton transfer, now I have a proton transfer. I'm going to make water as a good leaving group. And you might say, well, let's just lose water to make the cation. And we could, but I would prefer to actually push the water off with the adjacent oxygen. Use the adjacent oxygen's lone pair to make a CO double bond, pushing water away. And I'm trying to use reversible arrows for every one of these steps because this is another fun with acid problem. We have protons flying everywhere. There's no reason this mechanism could not go backwards. So I'm going to make sure that every step I show is reversible. So I've lost water. I've made what looks like a ketone with an R group on it and a positively charged O. And now I have, again, a good electrophile. I can add to the carbonyl carbon, and I'm going to add a second ethanol. We knew that we needed to do this because we showed you the product here. It has 2 OR groups on it. Here's the second OR group coming in, and that's going to be an arrow push just like we saw before, nucleophilic attack, pushing electrons onto the onto the oxygen. And we are one step away from our product now. You'll see that we basically have a protonated acetal after this step. So this is nucleophilic attack. This was loss of leaving group here. And lastly, I need to probably use some water or ethanol or even another, let's see, any of these species would be okay to use as a weak base to remove this final proton. So I'm going to use acetone because that is how I would start this mechanism again to turn another acetone into an acetal. And of course you see that I created water right here, so water is a byproduct, we'll put that there. And that is the acetal mechanism, so this is another proton transfer step. So let's go ahead and circle all these different types of steps. Proton transfer, nucleophilic attack, proton transfer, loss of leaving group, nucleophilic attack, proton transfer. Okay, so it looks really complicated and confusing, but it's pretty straightforward. We just need to make our ketone a better electrophile by protonating it. Then we attack with the weak nucleophile. We get the half acetal, we deprotonate it, we reprotonate it on the OH. A lot of students like to combine these two steps. Please don't do that. I want you to show the specific deprotonation step right here and the specific reprotonation step right here. And then we get to this intermediate, which can lose water as a leaving group, making this CO pi bond. That is another great electrophile. We can add our weak nucleophile ethanol again. That's a nucleophilic attack, giving us this, which is a protonated acetal. One final proton transfer step gets us to the product. One final thought I want to leave you with is that acetals can be used as protecting groups. Let's look at this situation. What if we had an ester and a ketone in the same molecule, and our goal was to selectively reduce the ester, and we'd get a molecule that looked something like this. So I wanted to reduce just the ester, and I know I need to use lithium aluminum hydride to do that reduction. But of course, we learned that lithium aluminum hydride will be happy to reduce this ketone at the same time or even before it reduces the ester. So what we can do is react our ester and ketone with a diol and a catalytic amount of acid. So you remember that we added 2 alcohols to a ketone to make the acetal. Well, here are 2 alcohols in the same molecule. So if we add these 2 to the ketone, we can make an acetal, and it would look like this. And if we set up the reaction conditions correctly, the ester should be unaffected by this reaction. So now I've created an acetal from my ketone. The ester is still available for reaction. This acetal is not susceptible to attack by Grignards. It does not react with bases. The only way to turn it back into the ketone is to add some water and some acid, and we'll basically do the reverse mechanism of what we just did on the previous slide. So now I can add my lithium aluminum hydride, and I can work up with actually H2O and H2SO4. That will both protonate the alcohol that's formed here, and it will remove the acetal, reforming my ketone. And so this will take me right to there. So I can deprotect after I've added the lithium aluminum hydride. And so the lithium aluminum hydride is a strong nucleophile. It does not react with acetals. We could use this in a Grignard reaction. I may have mentioned that a few seconds ago. If I wanted to add a Grignard to the ester but leave the ketone unreacted, I'd have to protect it as an acetal first, then add the Grignard. So let's look at that. We can do another option here. Let's say I wanted to add excess Grignard for my first step. Second step, again, water, strong acid. That will both protonate the alcohol that's formed from the Grignard. Remember that an ester plus Grignard gives us a tertiary alcohol, and the strong acid and the water will reform my carbonyl, giving me the ketone at the end of the day, along with the ester that reacted with the Grignard. So now I can react esters preferentially over ketones as long as I protect them. And it's easier to do the protection with this 1,2-diol because it reacts faster, because the second step, once I've added one of the OHs to my ketone, I have an intramolecular reaction to add the other one. So a ring closing reaction, as you see here we made a ring, is much faster than hoping that another ethanol wanders over to make the acetal with 2 separate R groups on it. So acetals can be used as protecting groups in a reduction reaction or in a strong base addition like a Grignard reaction.